Okay, guys, we talked last week about the whisper, and we said whisper stand for V for valence, S for shell, A for electron, P for pair, and R for repulsion. And we said as long as we have valence electrons, they will repel themselves. There will be a lot of repulsion among themselves. They are what? Negative charge, correct? Those particles, negative charge. We can expect whether they are a single bond or they are in single bond or they are forming triple bond or they are forming double bond or they are just by themselves orphan. We call them lone pairs or orphan pairs or non-bonding pairs. There still will be repulsion among all those setup of the valence electrons. So uh, whisper is a technique, correct, used to minimize this repulsion. Thus, the repulsion will continue until the molecules will obtain or will gain uh, geometry that minimizing this repulsion. Okay, and the best thing is to go through the to understand the whisper and how we determine the shape. And we said we have electronic shape and we have molecular shape, correct? Somebody will tell me what's the difference between them from last week. We mentioned that, correct? Do we? No, yes, yes, no. Is still somebody is still remembering? Somebody still remembering? No. Well, I think we did mention that, and let me just give you the here it is, guys. If you look at this, can you see this? You saw that last week or not? You did? No? Okay, so let's take a picture out of it and snapshot out of it, and then try to have it here. So the we'll not worry about too much because we will be dealing with the molecular geometry, not with the electron geometry. So it is. So what's the difference between those two geometries here? Is the electron geometry just very electron geometry will look at the whole molecule, considers the whole molecule, whether it's single bond, double bond, triple bond, non-bonding. For example, if I take H2O here, and I'll say, okay, the H2O, in order to get whisper, you have to have what? You have to have Lewis dot structure. Lewis dot structure is the backbone. Lewis dot structure is the backbone of whisper. In order to understand whisper or determine the geometry, you need the correct Lewis dot structure. So for H2O, this is H2O. We have option 6 valence electrons, and we said hydrogen always has only one electron here. This is hydrogen here. So if I look at the molecular shape, the molecular geometry will not consider all those 4 sets. We have 4 sets of valence electrons. One set is bonding, valence electron bonding, forming sigma bonding or single bond, correct? Two sigma bond or two single bonds, two sets of bonding valence electrons. And we have 2 sets here of non-bonding, lone pair or orphan pair, correct? So those are 4. That's electron geometry. The molecular geometry, we are not interested in considering the lone pair. We look at the molecule like this. And then we'll take goes out. So what looks like this is this is bent, correct? And this is the molecular geometry. Okay, guys? Geometry. Okay, guys, and this is 4 sets, correct? They will consider 2 sets, I mean, 2 single bonds. They don't consider what? Here, this, ignoring the lone pairs. They are not considered. Okay, guys? And here we consider all sets of valence electrons. So we have here 2 sets, and here we have 4 sets, correct? So the 4 sets here, the electron geometry here will be tetrahedral. This is tetrahedral and this is bent. So you can see the difference between them if you consider just the whole setup, lone pair, single bonds. You have 4 units or 4 zones, and therefore it's tetrahedral. While this is just, you are considering the single bond, double bond, triple bond, ignoring the lone pair, so the molecule will be like this. This is pent, correct? So that's the difference between the two, between molecular versus geometry. Molecular does not include the lone pair repulsion, ignoring the repulsion of the lone pairs, okay? And it's not considering the lone pairs. So, okay, I'll go for the next. Everybody has this? Everybody has this? Okay, so that's, we have to know a little bit of knowledge to know about this one here. So the next is to go to the code. Well, the code, it turns out to be, we have H2O, correct? So we will designate those. The central atom, this is central atom, equal to the core or the heart, whatever, I mean, of the molecule and of the geometry of the molecule here, of the molecule, correct? So that's really what really determines the outcome of the geometry is the central atom. Central atom does really determine the shape of the molecule, of the compound. So, and we are dealing with now all covalent compound, not anything with the ionic, just all covalent compound. So let's look at this, and we have here, if the compound is, if the atom is terminal at the edge, we give it a B. I mean, you can designate any alphabet, it's up to you, but B, regardless if they are identical or not identical, that's B. And the lone pair, we call them E and E. So the code, the whisper code of this molecule, code of H2O will be, guys, so will be central atom is 1A, correct? That's the A here. So A, that's the central atom. How many B's we have? We have 2 B's. How many lone pairs we have? We have 2. E2. So I have A, B2, E2, correct? Now I'm going to look at the table just for the molecular, not the electron geometry, but just the code for the molecular shape will be, let me go up here. First of all, everybody has this, everybody has this, everybody has it, everybody has it. Okay, let's take this one out. And now here we have the code. We have what we said H2O is A, this central atom, B, two terminals, and two lone pairs. So we can come and look at the what will be the molecular. This shape is the molecular one, correct? That's the molecular one. Okay, so where is it? Somebody will tell me where is it? AB2E2, H2O, correct? That is here the code. How many lone pairs? Two lone pairs, correct? How many regions we have? We have four regions, correct? Four regions. How we know the region or unit? So we call unit or group or region, that's the same thing. They are, look at them here. Let's count them here. We have 1 single bond, second single bond, lone pair, 1 lone pair, the second lone pair. We have 4 units for region, 4 zones. Okay, so we come back here, look at our code here. So we have it here. It's 4 zones, 2 lone pairs, 4 zones or units or groups. And this is the code here. And the shape of it has to be bent. The angle of this bent is 105. The question is it polar? Yes, it is polar. Why? Well, it turns out the presence of the lone pair on the central atom causes the molecule all the time, no exception, to be polar. So, presence of lone pairs on central atom causes the molecule to be polar all times. No exception, guys. Okay, guys, no exception. So, is this following? That's the first one. So let's take the second one here. It has this. It has this. It has it. Okay, let's take the second one. The second one here, we have the example here. We can go and look at the second example. BF3. BF3 here. BF3. Okay, guys. Well, we have to know what's the Lewis dot structure of it. Well, can we do that? Yes, we can. So boron is where 13 minus 10 is 3A, correct? Group 3A will have 3 valence electrons. So boron is non-metal, correct? Boron will have 3 valence electrons. And then the fluorine in 17 minus 10 makes 7. That's a 7A. There is 17, that's the modern numbering of periodic table. The old one is A and P. But the A and P is good in sense that will give us the sense of the number of the valence electron. 17 does not tell us the whole story, give us will not get anything about the valence electron number. So 7A, that's 7 valence electrons. So fluorine is 7, 2, 2, 2, 6, 1. This is 7 here. Here is 1, 2, 2, 2, 2, 2, 2. Another 7. That's here 1. And here another 7, 2, 2, 2, 2, 2, 2. So then we have to connect to make single bond, correct? That's that structure, we covered that. And we have to look at the CNOF Only CNF. We don't care about the other elements in the periodic table. Only those, they have to have what? Octet rule. So we have fluorine here, yes. We have to check fluorine all over. So this is 2, 2, 2, and 2. 3 sets of non-bonding, lone pair, orphan pairs, and 1 is bonding. So 1, 2, 3, 6, 7, and 8. That's so octet rule is good here. Octet rule is good. How about this one here? 1, 2, 3, 3 sets non-bonding, and 1 set is bonding. This is 8. Okay. So the fluorine is good. Boron, we don't care about boron. Okay. How much boron does it have? Somebody will calculate how much, how many valence electrons. How many? It has valence electrons 3, but how many now with this in the bonding itself? 3 sets of bonding, 3 sigmas, correct? 3 single bonds. 6. How many? 6. Does it have 8? We don't care about it. So we care about those 4 elements. They have to have octet. If they don't, then the structure is not correct. The structure, the Lewis-Dot structure is not correct. So boron, it's violate the octet rule. We don't care. And I will say all the elements can violate the octet rule except those 4. They are not allowed to violate. Okay. So now, what is the code of this? What is the code of this compound or molecule? B is the central atom. How many? How many central? A is the central atom. B is the terminals. B is the terminal. So the code will be A, B what? 3. Okay. So I'll pretend I don't know what the according to this code here, what will be the shape. So I will go back and look. I'll look back in the code area. Can you see it? It's very confusing, but what is it? Can you see it? It says what? Trigonal planar. So, correct? Can I take this one out? Maybe I'll. So this is a boron, fluorine, 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 and then fluorine has 3 sets of non-bonding. So we have A, B, B, and B. This is AB3. AB3, where is it? It's here, correct? So how many zones we have? How many? 3 single bonds, correct? 3 zones. 1, 2, 3. So 3 zones here. Do we have a lone pair on the central atom? No, no lone pair on the central atom. 0 lone pair, correct? And what's the shape of it? The molecular shape will be trigonal planar. What's the angle of the trigonal planar? Is 120. It is polar or non-polar. How we know? If the central atom has lone pairs, it will be polar. If it's not having lone pair, then we have to look at the terminals. So let's look at the terminals here and decide. Are the terminals equal? Yes or no? Yes. All of them are fluorine atom, correct? Since they are equal, so the molecule is symmetrical, and the molecule is BF3 is not polar. Why? Because it has similar terminal atoms, correct? They are similar. Everybody is following? They are really similar. So, but if I have something looking like this, guys, and this one is chlorine. Is this polar? Yes or no? Yes or no? Yes. Why? Why is it polar now? Because you have two identical, but the third one is not identical. Correct? As soon as you have one atom is not identical, then there will be polarity there. The molecule is polar. This is polar, not identical. Here, all the identical terminals. So, non-polar. Okay, guys. Let's take, it has this. It's inside the, let's take CCl4. This one. Carbon has 4 valence electrons. Chlorine, we have 4 of them. Chlorine is 7, 6, 7. And here is 2, 2, 2, 2. And here's 1, here's 1, 2, 2, 2, 2. And here's 1, 2, 2, 2, 2, 7. So start doing what? Connecting to make single bond. Always start with single bond. Single bond, single bond, single bond, single bond. So you ask yourself which we have to take care of, the octet rule, carbon, nitrogen, oxygen, fluorine. All the other elements we don't care. We have carbon here because we have carbon here. This is my A. Does it have 8? Yes. Why? It has 4 sets of sigma or single bond. 1, 2, 3, 4 sets. Each single bond made of 2 valence electrons. That's 8. 2 multiplied by 4 is 8. So A, B, 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 B. So this is AB4. Where is the AB4? AB4 is here. Does it have a carbon? Does it have a lone pair? No, no lone pair in the central atom. No lone pair. Okay, 0 lone pair. How many regions or units we have? We have 4 units or regions or zones. Why? Because we have 4 single bonds. Correct? So the AB4 is tetrahedral. Now it is polar or non-polar? Somebody will tell me. Is this one polar or non-polar? Non-polar. Why? That's correct. The answer is correct. Why? Because we have identical what? Terminals. Chlorine, 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 chlorine. Correct? Now, if I take the same thing here, chlorine, chlorine, and here's chlorine, and then I said here I'll put fluorine. Is this polar, this compound? Yes or no? Yes, because now I changed. This one is not identical. Those 3 are identicals, correct? But this one is not identical. This is polar. So this compound is polar, and this compound is not polar. And a tetrahedral has an angle of 109.5 degrees. 109.5 degrees. Okay, guys. SO2. SO2, let's take this one here out. Can I take this one out? Take it out. Okay, so let's go for SO2. We did the H2O. Let's take SO2. The sulfur is 6, correct? 16 minus 10 is 6, 6A. So the old classical periodic table A and B. So 16, the new one, the modern periodic table numbering. 16 minus 10 makes 6. 6A. So 6. So the valence electron of sulfur is 6. So let's put this one 6. I'll put here because oxygen likes to have always what? For octet rule, always 6 double bond. You can see this oxygen loves to be in what? In double bonds here. So this is 4, and we put 6 here. Okay. So now let's look at this. This is sulfur. This is oxygen. I'm boxing them with their valence electrons. So oxygen always loves to have itself to have octet, always in double bond most of the time, and nitrogen in the triple bond. So let's put double bond here, 2, 2, and there 2, 2. So guys, look at this. Does oxygen really obey? Does oxygen obey the octet rule? Yes or no? Yes. Why yes? Two sets of single bond of two single bonds make double bond, correct? Two sets of bonding pairs and two sets of non-bonding, correct? So two sets of bonding pairs and two sets of non-bonding pair. Each set is 2 electrons, so it makes 8, correct? You want to verify it? We can verify this. So 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is good. And the same thing with, that's good too. So you can calculate the same thing. So now, what will be the code of this? Somebody will tell me without looking. I mean, I know you have the result in front of you. This is your A. This is your B. This is your what? B. This is what? It's not it's a lone pair, E. So this is A, B2, E2, E1, E1, yeah. So now look at this. What is, how many zones, or say, how many zones or units or groups we have? How many? 3. 1, this is double bond. 2, another double bond. And the lone pair number 3. So this is 1, this is 2, this is 3. 3 units or whatever, units or groups or zones, correct? Now, I come here with this AB2E1. I need to get the shape. So therefore, my suggestion, since the exam will be open book, I'll print this one, this table here, or the whole PDF file. That's in your iCollege. Print it out and put it near you so you can refer yourself whenever it's asked about any geometry here. So you know, after writing the Lewis dot structure, you know what the shape will be. Where is this AB2E1? It's this one here, the code. 1 lone pair on the central atom. The central atom is sulfur. How many zones we have? We have 3 zones or groups or units. What the structure of this? Structure of it is bent. Remember, we don't consider this, correct? So this one will be looking like this. Bent. Okay, so bent. And the question is, this is because, remember that it has 3, the trigonal planar is 120, correct? 3 zones. It has 3 zones, correct? The 3 zones supposed to be what? Supposed to be a trigonal planar, but it's not a trigonal planar. It's not 120 degrees, correct? It is less because of the lone pair, correct? I'll show you what we mean by this. So, in a minute, but look at this. If they got this, it is polar or non-polar? Polar or non-polar? Non-polar or polar? Come on, guys. I know it is Monday today. I know, I understand fully. I understand that. I understand. Polar or non-polar? Non-polar. We'll open an option here. No. Open an option. No. Okay, no option. So this is polar. Why? Yes. Perfect. Perfect. Excellent. So that is lone pair. Lone pair will force the molecule or the compound to be what? Polar. Everybody's following here? Okay, so the last one. Everybody has this? Everybody has this? So the shape is bent, but it is, the degrees is, here is what is is 116, not 120, because the 3 zones it will have 120, but it's less. Correct? So, can I take this one out? Last one. Take this one out. Take it out. Okay, let's take the last one here, which is ammonia. Well, ammonia is now we have hydrogen always, that's no problem at the terminal. But nitrogen has how many? Where is nitrogen? Nitrogen in 15. Group number 15. Group from the top to the bottom, 15. 15 minus 10, 5. 5A as always will have how many? 5 valence electrons, correct. So it will have 1, 2, 3, 4, 5. That's perfect, correct. 1 hydrogen, hydrogen always 1, and 1 hydrogen, 3 hydrogens we have. So let's connect those. This is 1 single bond, this is 1 single bond, this is 1 single bond. Hydrogen always does not have octet rule. Maximum is 2 electrons, it can exceed 2 electrons, correct? 1 single bond. Cannot be connected to another atom with double bond or triple bond. No, always single bond. Now, what will be the code of this? Somebody will tell me. So this is our central, the core and the heart of the molecule. This is B, this is B, this is B, and we have 1 set of lone pairs. So A, B, 3, E, 1. A, B, 3, E, 1. That's really 4 zones, correct? 1, 2, 3, and 4. This is lone pair here. 4 zones. According to the 4 zones, this should be tetrahedral, but it's not a tetrahedral because of this lone pair, correct? So the lone pair will squeeze it a little bit. So here it is. It has AB3, E1, correct? 1 lone pair on the central atom. How many zones? 4 zones or units or groups. What's the shape of it? The shape of it is trigonal pyramid or pyramidal. Okay, guys. What's the angle? The angle is 107 degrees. It is polar or non-polar this time? Come on, guys. It has to be what? It has to be what? Polar. Why? Again, we have what? Lone pair on the central atom. Okay, guys? Now, I can show you the effect of the lone pair, correct? Will come the lone pair. So, can I take this one out? And then we have this one done. Can I take this one out? If they has it? Okay, so let's take this one here and then let's look at this one. We don't need it anymore. So let's look at the fact of this double or the mysterious behavior of the lone pairs. Very mysterious. So let's look at this. I have, if I go for this one here, so lone pair, no lone pair, correct? So this one here is no lone pair. So this one here will be what? Polar, non-polar? Non-polar, correct? Why? No lone pair first, and 2 reasons. 1, no lone pair on the central atom. And what's the second one? This is number 1. Number 2, all the terminals are what? Identical. If they're identical, that will be non-polar, correct? So all terminal atoms are identical. Now, I go from here, I put this one here, something look, and put chlorine here, for example. It is now polar or non-polar? This is non-polar, we say. This is non-polar. How about this one here? Polar or non-polar? Polar. Why? Although we don't have lone pair on the central atom, but we have what? 3 are identicals, and the other one is not identical. The fourth one is not identical. So this one has to be polar. This one is non-polar. So this is the one. We talked about the similarity, correct? Now let's look at the lone pair. Let's look at the lone pair, correct, guys? Let's take a look at the lone pair. So, can I take this one out? Can I take this one out now? Okay, now let's look at this. We can start with the same compound we started, methane, natural gas. There is no lone pair, correct? Now we'll introduce one lone pair. So E equals 0, lone pair is 0, E equal 1, correct? Now E here, E equal how many? 2, correct? 1 and 2, this is 1. This is 1 and 2. So lone pair is, oh sorry, it is okay, guys. So everybody is following me here. So what do you think about the polarity? So with the polarity here, which one the strongest polar among all those? So the angle here, is 107 degrees. The angle here is 109.5 degrees. And the angle here is 105 degrees. Okay, so what conclusion we can make? What conclusion we can make, guys? So if we have no lone pair and identical terminals, the molecule will be non-polar, correct? That's what we have. This is non-polar. We said polar because it has a lone pair. This is polar. But which one is more polar than the other? This is most. This is what? Least. So what is the conclusion here? The higher number of the lone pairs, the higher the polarity. So let's do conclusion here. I wish they have an iPad. Just writing like I'm writing on the wall, standing up writing on the wall. It's inconvenient. It's very hard to write. Conclusion. The higher number of lone pairs on the central atom, the higher number or the higher numbers of lone pairs on lone pairs. Let's make it with the real English sentence. So can I take this one here out? I'll make the conclusion later on. Just can I take this one out? Make it real English. Sounds like real English, not street English. No, not street English. So we want to make it real English here. So here it is, conclusion. The higher the number of lone pair found on the central atom is, the higher is the polarity. That sounds English, professional English, not street English. So that's the conclusion. It's very important. So now, if I have, and you can witness that yourself. So everybody has this conclusion. I apologize my writing. They said they're saying there's like chicken writing. Did you know what's this chicken writing? Yeah, chicken writing. That's a chicken writing. So I apologize for my chicken writing here. So anyway, so it's very hard because writing on a wall. So anyway, so everybody has this conclusion. That's not in your what? In your PowerPoint. That's not in the ebook. But I want you, if anything comes in the final exam, something like this, you are prepared. So everybody has it. As I said, this conclusion is not there. So, but this final exam can surprise you, and it can surprise you anytime things are not even, you have not seen, not heard, nothing. So let's take now the just the last thing, and then we'll go for chapter for the last thing of the chapter. I'm not going to chapter 5, but I'm finishing chapter 4 with small tiny topic. Yeah, we have plenty of time. So can I take this one out? Okay, now the last thing I want you to look at this, really give it a. We have here, correct? This is H, 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 and there is H. There's no lone pair, correct? Polarity is 0, not polar, correct? Then we have here X, 1, H, H, H. Then we have X, 2 H's. Then we have X, 1, 2, 3, and here is H. Okay, so we said what in the conclusion? The higher number of the lone pair found on the central atom, the more polar the. So the polarity here will be, which one the greatest one? So this one here, polarity is 0, we said, correct? So this one here, this one the highest polarity, correct? Why? E3. Here is the lowest. Here is the lowest polarity. Why? E is what? 1. Here is moderate polarity. And then, because this, we have to take this E. E2, and this here, the highest polarity, and E is 3. So you get the idea now? So, and here, and let's look at something, another, from other point of view. This is 2. Now, if this is 4, correct, 4 regions, the angle here, now we are looking at the angles. Let's take another color here and look at the angle here. The angles here. We are looking at the angles here. Here, because this is 4 zones, all those are 4 zones, correct? So this angle here will be around 4 zones, correct? Around 109.5 degrees. The presence of the lone pair will decrease this one here to 107 degrees. More lone pair will decrease it even further, 105, correct? And how about 3? Will what? What will do with it? Yes, around 103 to 100, 100 degrees, 101. Not degrees Celsius, degrees, sorry. You can see the angles is becoming less and less with the number. The polarity will go high, but the angles will be less and less and less, correct? So you can see the higher number of the lone pair, the higher is the polarity, the lower is the angle, correct? That's what it says. So higher number of E equal higher polarity equal less angle. So this is another brief or short summary of what we have this. So everybody has this? Everybody has this? Okay, everybody has this? Okay, good. You are very quiet, but it's okay. I can understand. It's Monday. It's Monday. It is Monday. So everybody is very quiet. So, but don't sleep on me, please. So last topic here, we are looking at type of intermolecular forces. We are looking at intermolecular forces. We have 4 types. The first type called dispersion. So intermolecular force, I'll say IM. Here it is. IM. Dispersion, IM. Meaning intermolecular forces. Well, dispersion is the fact that it's happening within nonpolar covalent bonding. It happened because the valence electron being dislocalized. Okay, so VEs are dislocalized. So they are not. You have seen this one here. There is. I don't have, but if you look at this here, sometimes if you have a small tank, you can do an experiment here. This is a piece of paper here. Okay, so if you rub, we'll take a small tiny piece. You might not be able to see it, but you can see it here. So if you rub so this made of polymer. Okay, by rubbing it against my hair or against my head, I'm dislocalizing what the valence electrons of this polymer, whatever its carbon may be, whatever the compound is here inside. So by doing this, and I've tried to get, you'll see this is but what will happen is this will come because of the localizing of these valence electrons. One area will be positive because losing this electron. One area will be positive and negative because the electron will come to it. So you get something like static. What we call this one here, static, correct? Static forces. So this called here dispersion dispersion intermolecular forces between molecules. Are you following me here? Let me just give you an idea. If you hit your elbow against a hard object, what will happen? You will feel like electrical, correct? You feel like electrical current going through your elbow, through all your hand. You feel it there. What's happened is the hit or the collision of your elbow with that hard object had delocalized the valence electrons of your material of your elbow here for a few seconds, and then those you are generating one area is empty from this valence electron, one is those electrons jump to that area. So let's look here. I'll give you an idea of this, what's happening. So here it is. So you have here, this a normal atoms. Okay, so then you have collision here. Now, instead of having this, one electron here is here called a hole, and here this electron will jump into this area in the second row. So this one will be missing, like partially positive. This one is, you add this electron to it for a few seconds, partially negative. So the electron, the current, electrical current will go through. The electrical current is nothing less than just the transfer or moving of those valence electrons from one side to the other side, correct? From one side to the other side. But that's what we call it dispersion. So dispersion always happened in non-polar covalent bonding. So, okay, guys, that's a dispersion. So if I have two molecules for methane here, methane and methane and methane and methane here, and there's another molecule here. There's another molecule here. This is nonpolar, okay? And this is nonpolar, this is nonpolar. So what's happened is those two molecules will come, if they collide against each other, they will have a force among themselves called dispersion or static intermolecular forces. That's the first one. The second one is can I take this one out, guys? Can I take this one out? That second one is called the dipole intermolecular forces, IM, intermolecular forces, F, IMF. Okay, yeah. So what's happened is, if I have polar covalent, you have to have a polar covalent in polar covalent bonding. So I have here, for example, hydrochloric acid. This is hydrochloric acid, correct? HCl. And we have here another HCl, two molecules of HCl, okay? Or you can say this is HF, whatever compound, two molecules, correct? They have not to be identical with each other. Say they can be different. So it is. I can make here hydrofluoric acid. That will work. Another hydrofluoric acid here. So what's happened is the most electronegative. This is the most electronegative. Most electronegative atom. This is here, and this is here. Okay, so what will happen is this electron here, those are making single bond, and remember here, and this goes here too, and this one here too. So what will happen here, there will be partial dislocation of the valence electron. So starting from here, this valence electrons will be pulled by most electronegative atoms. So it will be looking. So this is the, we say, this is the start of the dipole. Start, that's the end of it. The beginning and end. So beginning and, so this is the dipole. Okay, guys. And here is positive, correct? Here does not have even. So, but you will see this partial here will be pulled by the chlorine. This one here is will be pulled this way here to the most electronegative atom. This one will be pulled, and between this here partial here, that will be make it here partial so you can. So all in all, this molecule here, the dipole starts from the least electronegative towards what? The arrow will end to the most electronegative atom, from the least to the most. Correct? So this is the interaction between those two here, between those, for example, two here, or the three ones. Even this one here can be pulled by the chlorine atom, correct? So if you look at this, this is called dipole between two dipoles. I put just more than one, more than two, I put three. But anytime I have polar covalent compound or bonding, so those the interaction between them will be dipole electromolecular forces, correct? Well, the most electronegative atom will pull in towards itself this valence electron of the least electronegative atom. So number three, can I take it out? Number three, we have hydrogen bond. Hydrogen bond. Well, hydrogen bonding is nothing mysterious about it. We have hydrogen. This hydrogen can connect itself to nitrogen atom, or can connect itself to oxygen, or can connect itself to fluorine. Okay, that's the same thing with CNO. Remember the CNO? But here carbon is missing. But here is, you have this, and this. Those three here will be making with hydrogen. This is a hydrogen bond. You have a hydrogen in common, and the hydrogen will connect itself to nitrogen electronegative atoms, all those electronegative atoms. This is number one. This is number one. This is number two electronegative atom, two. This is three. So, most electronegative atoms. So, and that's what we call hydrogen bonding. This happens in whenever you have hydrogen and nitrogen. For example, let me show you here. I have H2O. H2O has hydrogen and oxygen, correct? Oh, sorry. I apologize. This is hydrogen. Well, can I make hydrogen bonding of this? Yes, plenty. So maybe three of them. So let's do here. The first one, I can take this hydrogen, connect it to another molecule of H2O. Here it is. It's another one. Okay, I can take this one here and then connect it to what? So now I have how many here? Three, correct? So let's see here. One, two, and then I have, this is not clear here, so I'll do it much better so you can follow it here. And this is O, This is number 3. This is 3. So between oxygen and hydrogen, or oxygen and nitrogen, correct? Can I make it different? Yes, I can mix Windex. Windex is hydrogen, H2O, with ammonia. So ammonia will come here, H, H, and H. So this is the bonding here between those two here. This one here, and the bonding between oxygen. So everybody following here? So this is anytime the hydrogen will bond itself with nitrogen or oxygen or fluorine, I get hydrogen bonding. So the more hydrogen bonding you have, the more stable the compound. This is very important rule. So the more hydrogen bonding is found, the more or the most stable the molecule. That will affect what? That will affect physical properties, such as boiling point will be very high. Boiling point increases. So the boiling point will increase. So the more hydrogen bonding you have in a molecule, correct? The more hydrogen bonding you found in the molecule, this molecule can expect it to be very stable, and the boiling point will be very high, correct? Compared with the one that have less or least hydrogen bonding. The last one here is, as you know here, the last one is the ionic, and that's we know that's the highest. So number 4, ionic, IMF, intermolecular forces. Well, ionic here between ionic compound or bonding, ionic bonding. Ionic bonding or compounds. This by far the most strongest intermolecular forces, the most strongest IMF. Okay, guys, so I have sodium chloride here. That's positive. Chloride is here. So you have another molecule. So they are connecting themselves with really ionic compound is very, very very strong bonding between the cation and the anion. So let me just make the comparison between all those three. Can I take this one out? Comparison. The IMF, intermolecular forces, IMF, intermolecular forces, ionic bonding greater than hydrogen bonding, and this is greater than dipole bonding, and greater than dispersion bond. So this is just the when you order them in order, which is from, this is the highest, this is the highest, and this is the lowest. Okay, guys, that will conclude chapter what they call it, chapter 4, and I'll put tonight for you quiz number 2. Quiz number what? 2. So um, I will stop recording here, and then we can record for chapter. We have plenty of time to do the next chapter. So stop here recording.